look here. All right, so what are we going to do? We want to, let's skip part A. We'll just assume at that point. How would I do part A? Plug it in. Yeah, just plug it in and just, it should make the equation, it should satisfy the equation, make it work, right? Okay, so part B, we need a tangent line here. What am I going to do for part B? Take the derivative, good. All right, so I've got the x's and the y's are kind of tight. It's not solved for y explicitly, right? So I'm going to have to just differentiate with respect to x. I'll just implicitly differentiate. What's that going to give me for my first term there? What am I going to get here? Say it again, Gabe, go ahead. There you go, good. Derivative of sine hand is cosine hand times the derivative of hand, in this case, derivative of y with respect to x. There's our y prime. Second term plus 2 equals, how about third term? There you go, 2y y prime. So where should we probably, well, actually, it doesn't ever ask us to solve for y prime, does it? It just wants a tangent line. So what would I probably do next here then? I can't do that. I'm trying to solve for y prime, right? But do I really need to isolate, like, do I need to go through the steps of pushing everything to one side and... Yeah, let's evaluate right now, right? Because we don't need to ever actually write out the expression for y prime, the algebraic expression. It's not asked for, right? And all we're trying to do is find a tangent line. So let's plug in the values of x and y right now, which will make it easier to solve for y prime, okay? So cosine, if we're plugging in pi for y, cosine of y would be what? -1, right? And of course, we just look at unit circle on that, don't we? Right? Pi is right there, and cosine's the x coordinate, so it'd be -1, wouldn't it? So we're getting negative y prime plus 2 equals, plugging in pi for y, right, equals 2 pi y prime. So probably just push the y prime turn to the right and then factor out a y prime and solve for it. Right? Everybody agree? Okay, so I'm going to get 2 equals 2 pi y prime plus y prime. So couldn't I just do that? Give me thumbs on that. Does that make sense? Okay. Divide each side by 2 pi plus 1, and we got it. So y prime equals 2 over 2 pi plus 1. So we've got the value. And notice that's a number, right? There's no variables in there, just constants. So we got the value of y prime. We know the values of x and y. So now we would just use point slope, right? We get y minus pi equals m, which is right there. Oh, excuse me. M times the quantity x minus pi squared over 2. That's it. And I mean, if I really wanted to clean this up, I could distribute this to both parts and add the pi to the other side. But that's the equation of the line right there. It just didn't point slope form. Okay? We good on that one? Okay. All right, how about something like this now? Take a second and think about that. How are we gonna find those points we're looking for? We're looking for the points where this curve has horizontal tangents and where it has vertical tangents. Any ideas for strategy here? Lucy, you got an idea how we could approach this one? Okay, right. Everybody agree? Now, this is going to be a derivative issue, isn't it? Because if we want to know where we have horizontal tangents, what's happening when we have horizontal tangents always? What would be true there? Everybody, you see that would be where the slope is 0, right? Where I have 0 slope, that means the slope of the tangent to the curve would be 0, which would be horizontal. And a vertical tangent line would be someplace where the slope is undefined, right? The slope of a tangent to the curve would be undefined there. So this is going to be a derivative issue. We're just going to have to find the derivative and then analyze the derivative to see if we can determine where those things are happening. All right, let's try that. So again, the x's and the y's are all tied up here, so we're going to have to implicitly differentiate again. First term, what am I going to get there? Okay, 36 plus 18 y prime. Okay, there we go. 18y is the first link in the chain, right? Times y prime. Derivative of y would be y prime equals 0. So I got to solve for y prime. So let's push all the non-y prime terms over to the right. Factor out a y prime on the left. We probably could skip this step, but I'll go ahead and write it. Something like that, right? Divide each side through by this factor. And we get y prime equals negative 8x divided by 18y plus 36. And it looks like I could simplify that a little bit. If I wanted to factor a 2 out of the top and bottom and simplify, I could do that. But I'm not even going to bother. We'll be able to answer the question either way, right? So now can anybody tell me there? I've got a rational function here, right? I've got a fraction. Where would any fraction equal 0? What's happening in a fraction when it equals 0? The numerator is 0, right? 0, we get 0 on the top and not 0 on the bottom. Okay? So the conditions where this would be equal to 0 would be when negative 8x equals 0. So when x equals what? 0. Okay? When x is 0, the numerator is 0, and therefore the slope is 0. So now they want us to find the points. So how am I going to use that information to find the points where that's happening? And it could be there could be one point, there might be multiple points. What could I do? Yeah, I got to plug that 0 back into the original equation, right? Because I know that the condition for a horizontal tangent is when x is 0. So if I feed that back into my original equation, what's going to happen then? I'm going to get 36y plus 0 plus 9y squared equals, that's probably not good. Oh, of course. Of course. Okay. So if we plug that in, we got the equation. (36y plus 9y squared equals 0. Okay, so now what? What do you think, Shay? What are we going to do next here? So when x is 0, that's the equation that we get. Yeah, good. We solve for y. Good. Could we clean this up a little bit? 9y. Okay, good. So we factor out a 9y, and then we're just left with y plus 4 equals 0. So what are my solutions then? When x is 0, what are the values of y? Yeah, there you go. Okay, so we get y equals 0 or y equals -4. So all that stuff is telling us then that we have horizontal tangents at the points x is 0, y is 0, or the point x is 0, y is -4. Okay, give me 1 to 5. Is that making sense? Okay. Good. All right, now, Cahill, what about the second part of this? We need to find where we have vertical tangents. What are the conditions going to be of this fraction when we have vertical tangents? We said that's where the slope is undefined. Set y to 0? No, close. Set the denominator equal to 0, right? we'd have an undefined slope when we had a number divided by 0, because we can't divide by 0. And think what that corresponds to. Going back to our limit stuff, if we took a limit as the bottom approached 0, we'd be getting an infinite slope. It'd be positive or negative infinity, so that would give us our vertical tangent line, right? But really, all you got to think about is just 0 on the bottom is undefined, right? So part 2 would be y prime is undefined when the bottom 18y plus 36 equals 0. So what value of y is that? Negative 2. And I could do the same thing, right? If I plug negative 2 back into our equation for y, original equation, if I plug negative 2 in for y, I end up getting what? Negative 72 plus 4x squared plus 36 equals 0. So in other words, 4x squared equals 36. So x squared equals 9, right? So what are the values of x? Plus or minus 2. Good. Or plus or minus 3, sorry. I'm attributing that to our bumpy bus ride. God, our bus was so bad last night. Coming home, I mean, going there too, but you noticed it more coming home. The thing just shook all over the road. Nobody could sleep. Everybody had a headache. It was terrible. Oh, I got to bed about 2:30 last night. Okay, so we'd say then that we have vertical tangents at x equals plus or minus 3 and y equals negative 2, right? So we get the points negative 3, negative 2, positive 3, negative 2. And we should be able to see this if I graph this guy on Desmos. We should be able to kind of see visually and just check this out, make sure we got it right. One really nice thing about Desmos is you can graph non-functions, which is hard to do on a TI-84. Okay. So there's our curve that we're graphing. We just type it in just like that, 36y plus 4x squared plus 9y squared equals 0. Okay, so it gives us this ellipse. And we want to check our points just to make sure. So we had points at negative 3, comma, negative 2. Positive 3, negative 2. And sure enough, those we can see those are the places where we have vertical tangents, can't we? Right? Okay, there's our vertical tangents. And then we can see also that at 0, 0, and 0, negative 4, I mean, can't we see pretty easily there that we're getting our horizontal tangents there and there? I won't even put them in there. No need, right? But you get the idea? Okay? All right. I'm going to skip this one for now, just so I can maybe get back to this. I just kind of wanted to get through this today. So we kind of started talking about this the other day, right? Here's our goal on this one. This is kind of cool. We're going to use implicit differentiation to come up with a new derivative rule. We want to come up with a derivative rule for logs, okay? We don't, obviously that's what we're trying to come up with. We don't already know it, but we do have a derivative rule, the inverse function of a log function, which is an exponential function. And we'll review this stuff. I want to take a day, probably won't be, maybe next time we meet, we'll just go through and do a quick review of exponential and logarithmic stuff, and particularly logs, talking about some of the properties of logs that turn out to be pretty important for us in calculus. We're going to take advantage of some of these properties when we differentiate really tough problems, and they work in our favor. So that's on the docket here for next time. But let's get to a point where we can at least come up with a derivative formula, derivative rule for logs. Okay, so we know that the definition of inverse functions, and you guys saw this, you watched that little video, right? The definition, that 11-minute video. If you haven't, that's one I want you to watch. Inverse functions, what's it mean to be an inverse relation? All it means is you're just swapping the domain and the range. The x and the y values get interchanged. Do you remember what the trick was for how you graph an inverse? Let me add a page to this here. So what I mean by that, just from that little video, I'm going to quiz you here for a second. So if I've got some function, doesn't even have to be a function, it could be a relation. How do I graph its inverse? Swap the x's and the y's. Okay, what kind of symmetry is there? Do you remember? Not the origin. So let's just say, for example, that I want to graph the inverse tangent function. Or let's graph how about if we graph let's take this one. Take this. Here's our example. Let's take the original function y equals x cubed. Okay? We want to find the inverse of that function. Okay? In fact, I'm going to write it using function notation. This is probably worth doing just a little quick review here. That's it. Good. That's going to be when we graph it. Okay, so how do I find the inverse here of this function? Remember the steps? Okay, so steps. We're going to, first of all, and this one seems like a dumb one, but it's useful. Replace the function notation with a y. Okay, so first step is we're going to write this as y equals x cubed. What's next? Switch the variables. You flip the x and the y. You exchange them, right? So this becomes an x. That becomes a y cubed. Now what do you do? Solve for y. Good. You solve for y. So we switch the variables and we solve for the new y. What's the one step required to isolate the y there? Cube root. Yeah, and when I take an odd root, I don't have a plus or minus, right? So I just get the single solution, y equals the cube root of x. And so we could call that, how about if we call it g of x? right? Or if we wanted to, we could use the inverse notation. Inverse of f equals cube root of x. Okay, so if I graph the original function, would just look like this, wouldn't it? A cube, y cubed would just look like something like that, right? There's y. If I graph, or there's f of x. If I graph g of x, yeah, it's going to have symmetry about the line. Whoops, wrong color. It's going to have symmetry about the line y equals x. Okay, doesn't that make sense? Because if I'm just going to flip the variables, like if I take a point, for example, if I take a point over at 2, 8, okay, that makes sense. That's a point on my original function. When x is 2, 2 cubed is 8. So we've got this point up here with coordinates 2, 8. Doesn't that mean that the point 8, 2 must be on the inverse? Those are the points that are linked, right? So that point's going to be right over here. Okay, well, that's going to be that way for all of the infinite points that form my original yellow function. They're going to be paired up with points where we flip the x's and the y's, right? Now, where are those points going to overlap? When x is equal to y. So that's going to be the place where they're going to, when they fold over this line, essentially, to form these inverse graphs, those are the places that are going to reside on the fold in the paper. Okay. So yeah, so we're just, the goal here then is to just flip this thing over the line y equals x. That's honestly kind of tough to do because we're used to folding things over, reflecting things over horizontal and vertical lines pretty easily. But rarely do we ever do something like this. So there's a little trick that I'll remind you about. It was in the little video, but I'll remind you about it. This is kind of a good one. And it just seems to always work. It's just a rule that it works. You can break this into 2 simple steps. If you want to graph an inverse, you're going to rotate the graph 90 degrees counterclockwise or about the origin. So if I did that to my yellow graph, I would get something like this, wouldn't I? If I rotated at 90 degrees, it would look like something like that. And then you reflect it over the y-axis. You do them in that order. You rotate 90 degrees counterclockwise and then reflect over the y-axis. And sure enough, you get what you're supposed to get. Whoops. Right? That's the graph of the inverse. Okay, makes sense? And they have symmetry about this line y equals x. And what's the test for inverse functions? How could I test whether f and g were inverses? What would have to be true if they were? This is a real important feature of inverses. F of g of x would equal, you got the right idea, it's not 1. No. It would equal x, because they undo each other, right? So we'd have, if they're inverses, 2 things would have to be true. Remember what that means? IFF? That means if, it's not if, it's if and only if. That's our symbol for if and only if, right? What does if and only if mean? If and only if means it's a 2-way arrow. It's a biconditional statement, right? So you could read it either direction and it would have to be true. So f and g are inverses if and only if 2 things are true. F of g of x equals x. So essentially what they're doing is the f is canceling the g, and we're just left with what's inside the g, which is an x, and g of f of x equals x, right? Does that make sense? So that's the probably the hallmark characteristic of inverses is that they undo each other. That's the nature of inverses, is they undo each other. Okay, which is why it's so useful for us to use inverses algebraically. Like if I wanted to, if you go back to pre-calculus and you wanted to do something like this, right? Like if I wanted to solve, if I want to solve that, what do I do? How can I unlock, like how do I isolate the x's there? You remember that? How do I unlock an exponential or undo an exponential function? Yeah, I do the natural log, because natural log and base e exponentials are inverse functions, right? So that's how I undo the exponential. Right? I get that. And then the natural log cancels the exponential, and so I end up with the equation 2x equals the natural log of 4. Just divide each side by 2, and there's my answer. Okay? And that could be simplified in a way that we'll talk about next time when we rehearse our properties of logs. You probably forgot, I would guess. So, does that make sense? Okay. When are we out of here? 25? Okay, maybe we'll just take a second here and let's look at one more example. So, okay, I got one for you. Okay, are those inverses? Gabe's saying no. How come? Okay, good. Okay, remember in the video, right? Those are not, and we can prove it, right? All we have to do is a simple test. Let's try the test for inverses. Let's try evaluating f of g of x and g of f of x. If I do f of g of x, that would equal the square root of x quantity squared, right? Which is equal to, well, you tell me in a second what that's equal to. So let's flip it around. G of f of x square root of x squared. Well, what is the square root of x quantity squared? That is x. Okay, so that seems to work. Check. So far, so good. It passed one of the two tests. What is the square root of x squared? Do you remember? Well, okay. I mean, close. It's the absolute value of x. That's where that plus or minus comes from, right? And so that one fails. That is not x. The absolute value of x is different than x. So it fails the test for inverses, and we just proved that they're not inverses. Okay, and they're not. They're not, because if I look at the graphs of these, this graph has a restricted domain and range, and this one does not, right? It doesn't have this one doesn't have a restricted domain, and so for them to be inverses, the domain and the range get flipped. That would mean that the range of this one would have to be unrestricted, and it's not. It is restricted, right? So the domains and the ranges really aren't interchanged there, okay? Without having both the square root of x and negative the square root of x, it wouldn't work, okay? All right, so then back to business. Whoops, back to business here. So back to this. So I don't know if we're going to finish this part or not. Hopefully we will. So we've got these inverses, right? I know that y equals log u. That is, its inverse would be x equals, or not x, u equals log y, right? That's one way of saying it. That is not very helpful, but what might be helpful would be to rewrite this function as an exponential, okay? Because we can always do that, right? We can always rewrite functions, log functions as exponentials and vice versa, and we can do that a couple ways. We can do it by remembering the statement, a log is an exponent, right? So whatever the log is equal to, in this case y, becomes the exponent when we write it as an exponential function. And the base stays the same. Well, what's the disguised base of a natural log function, right? We know that when we say natural log, that's really a base e log, right? We just are lazy and don't write it. Okay, but everybody agree that natural log of u is the same thing as the base e log of u, right? Is that making sense? Okay, that's just our special, we give special notation to base e because we use it so frequently for reasons that you'll see here shortly when we review this stuff. It's a very important number. It's kind of like pi. It's the natural number is a hugely important number. Shows up in the growth of natural systems all the time. So, so we could remember a log is an exponent. So whatever the log is equal to becomes the exponent. The base stays the same. And then the exponent's equal to whatever's left over, which was what's inside the log. Okay? Or we could use what we just did a second ago. We could do this, right? We could exponentiate both sides to unlock whatever the u is, right? Does that make sense? To rewrite it in this form. So e to the y would equal e to the natural log of u, and those are inverses, so they cancel. Either way, I get this. I get u equals e to the y, okay? Well, we do know how to differentiate that, don't we, right? That's no big deal. If I implicitly differentiate here, if I differentiate both sides of this, I'm going to get a u prime on one side. On the other side, I'm going to get derivative of e to the hand is e to the hand times the derivative of hand would be a y prime, right? So then if we solve for y prime, we just get y prime equals u prime divided by e to the y. But what is e to the y? Y was originally defined as log u, right? So e to the log u is just u. So I get u prime over u. There's my rule, right? We just came up with the derivative rule for logs. Okay, it's just this. Okay, there it is. So if y, oh, never mind. That's if we enclose the absolute, the argument of the log in absolute values, the rule still holds. And sometimes we do that just because, remember, the domain of a log function has to be positive numbers. You can only input positive numbers, and so sometimes we do that. But here's our rule. Do I ever write it here anywhere? Well, I guess it's right there. Here, let's write it one more time. So the derivative, let's summarize this. Here's our new rule. The derivative oh, hang on, give me 30 seconds or less. The derivative with respect to x of log u just equals u prime over u. There it is. Okay? That's what we came up with. All right. See you tomorrow.